This is part 6 of a series on gradient boosting method. In this video, we will implement GBM classification in code. This video was produced in Korean and translated into English, and my voice was generated through AI, text-to-speech. In the previous video, we analyzed the GBM classification algorithm in detail. In this video, we will follow the algorithm step by step and implement GBM classification in code. Let's implement GBM classification using scikit-learn's DecisionTreeRegressor. GBMs learns from real-valued residuals rather than target classes. Therefore, we need to use the DecisionTreeRegressor instead of the DecisionTreeClassifier. And we will also do the same using scikit-learn's GradientBoostingClassifier. And let's compare the two results. In GBM classification, log odds values are converted to probability values. The conversion function is defined here. This is a logistic function. And the data we will use is like this. There are two features X, and the target class Y, 0 and 1, for binary classification. We generated 200 pieces of this data. The depth of the tree is set to 2, and the number of trees is set to 50. And the learning rate is set to 0.1. Step 1 initializes the log odds F value. The initial log odds F is estimated by this formula. We used the mean of the target Y as the initial Y hat value. And initially, the log odds value of the previous iteration round is set to the initial value F0. Repeat the process below 50 times. Step A in step 2 calculates the residuals for all data points. The residual is the difference between Y hat from the previous iteration round and the actual target Y. The Y hat of the previous round is calculated with a logistic function using log odds. Step B of step 2 creates a regression tree and fits the tree to the residuals calculated above. The leaf nodes of this tree contain the average value of the residuals. When the predict function is called, the average value is returned. But we need the gamma value, which is the leaf value. So, let's change the value of the leaf node to the leaf value, gamma, so that when the predict function is called, the gamma is returned. This is a bit of hack to make the predict function return gamma. Step C of step 2 calculates the leaf value, gamma. First, find the leaf node ID to which the data X belongs. You can use the tree_apply function in this model to find the leaf node ID. Next, we read the leaf node ID one by one, and replace the value of this leaf node with the leaf value, gamma. The formula for calculating gamma is as follows. We calculate the gamma using the residuals and Y hat values of data points belonging to a leaf node. And step D of step 2 updates the log odds value, FM, with the new value. For example, in this tree, leaf node numbers are assigned this way. Here, we replace the value of that leaf node with the leaf value, gamma. And save the trained model in the models list. Calculate and store the loss to ensure that training is progressing well. Here, the loss is the binary cross entropy. And step 3 predicts the class of the test data. We randomly generated 1,000 pieces of test data and set the log odds of the previous round to the initial log odds F0 of the training data. Using the 50 trees created during the training process, the output value of each tree is multiplied by the learning rate and all are accumulated. This is the predicted log odds value, F, for the test data. The predict function returns the gamma value. Next, we convert this predicted log odds to probability values using the logistic function. If this probability is greater than 0.5, we predict the class Y as 1. Otherwise we predict the class Y as 0. The loss history calculated above is like this. We can see that the binary cross-entropy loss decreases well as the iteration progresses. And then we visualize the training and the test data to check the results. This time, we will implement it using scikit-learn's GradientBoostingClassifier library. The number of base models is set to 50, and the learning rate is set to 0.1. And the depth of the tree is set to 2, the same as the previous code. We fit this model to the training data, X and Y, and predict the class of the test data. You can see that GBM classification can be implemented very easily using the GradientBoostingClassifier. However, we used DecisionTreeRegressor to further understand how the algorithm works. Now let's visualize these two results and check the results. We'll then visualize the first trees generated from both models to see if they match well. Now, let's check the results. On the left is the result using DecisionTreeRegressor. And on the right is the result using GradientBoostingClassifier. Yellow is the training data, and red and blue are the test data. You can see that the decision boundary for this data looks like this. The decision boundary on the right is also the same. You can see that these two results match well. Now we will compare the appearance of the first trees generated from the two models. The split point of the root node in the left tree is 0.243 of the feature x1. The result on the right is also 0.243 of the feature x1. In this way, you can see that all split points are the same. And the leaf nodes contain the leaf values, gamma. Originally, each leaf node in this tree contained the mean of the residuals. But this was forced to change to the leaf value, gamma. You can see that all the leaf values of both trees match well. Let's run this code. The result is like this. You can see that the decision boundaries of both results are the same. And the trees are also the same. This time, let's implement SGBM classification. We will also use the DecisionTreeRegressor. This is very similar to the previous code. So, let's take a quick look at the changes. Sample the data at each iteration. The sampling rate is set to 50%. The subset size is smaller than the training data size, and the sampling is performed without replacement. We then calculate the residuals for the sampled data, and we fit the model to the sampled data. As such, only the part where sampling data is used has changed. And predict the class of the test data. This code is also the same as the previous code. This time we will implement SGBM using GradientBoostingClassifier. Set the sampling rate to 50%. The rest is the same as the previous code. Let's check the results as well. You can see that the loss decreases well as the iteration progresses. For DecisionTreeRegressor, the decision boundary looks like this. And for GradientBoostingClassifier it looks like this. Because of subsampling, the two results are similar, although not exactly identical. Let's run this code as well. The results came out like this. So far, we have implemented GBM classification following the algorithm step by step, and verified the results. In the next video, we will look at multi-class classification.